Wang, and he'll talk about spectral study of the interplay among lattice, spin, and electron degrees of freedom in a strong correlated polar metal. Okay, Wang, uh,
Thank you.
platform is yours.
Hi, everyone. Today I'm going to talk about the interplay among lattice being an electron in a strong correlated polar metal. Before I start, I would like to thank our collaborators at Penn State University and appreciate the funding source of Department of Energy and National Science Foundation for financial support of this study. As we all know, the interplay among charge, lattice, and spin are very important in material science, and they give rise to novel properties such as superconductivity, quantum information processing, and multiferroic material system. And today I would like to introduce you to a polar metal system called calcium rusinate 327. And it hosts ferroelectric-like distortion and metallicity at the same time. So if we zoom in at the low temperature range, we have mainly a very rich physical phase systems with 3 transition temperature, one at 56 Kelvin, that's a near transition temperature, one at 48 Kelvin, that's metal to insulator transition. And the other one is a weird one at 30 Kelvin, that's a electronic transition from insulating back to metallic. But in this study, we showed that all the low temperature phase there is a pseudo gap opening, and the crossover effect is actually a temperature dominant effect. At the same time, we can probe the lattice order with a optical technique called second harmonic generation that's sensitive to central symmetry breaking. And we can show that across all the temperature range, the system is a polar structure. And we have some transition feature that matches very well with the metal to insulator transition as well as the crossover transition at 30 Kelvin. Then I would like to direct your attention to photonic excitation of lattice order, namely the phonon spectroscopy probed by Raman. So we can see at low temperature, the blue line has a very large reduce of phonon energy, which is rather unexpected because if we consider the thermal expansion at low temperature, you will expect a smaller lattice parameter inducing a larger energy in phonon. But here the trend is kind of opposite. And this has been observed in the literature as well. And for example, in this literature, the dotted line are the experimental results, and the green line is just conductivity. Basically, in this paper, they claim this renormalization of phonon energy is due to the electronic property at the metal to insulator transition. And in the other paper, they did a calculation on this phonon mode, which points to a breathing mode that's sort of modulating the octahedral cage, which induce a redistribution of charge orders in the orbitals. However, I would like to point out that this theoretical calculation is not from first principle, and they cannot distinguish low temperature phase versus high temperature phase. So in the following presentation, I'd like to argue the other interpretation of this phonon peaks, mainly because we have some experimental observation near the phase transition that clearly shows a Schur peak arising near the phase transition. At the same time, we resort to DFT calculation with LDA plus spin optical coupling with a noncollinear scheme, which can differentiate AFM-B phase versus AFM-A phase. And as you can see from the results, the prediction also shows a large renormalization of phonon energy, but to the opposite trend. So combining those two evidence, we try to propose a different fitting model of this phonon modes that actually composed of two different peaks. So as we show here, the cyan color peak and the blue peaks are interpreted in this spectral regime. And if we compare to the DFT calculation from the left-hand side, the overall trend agrees with the DFT calculation, even though for the cyan peak, we have a larger energy shift predicted from the DFT, but experimentally, we don't see that. But the energy shift trend agrees fairly well with the DFT prediction. At the same time, very interestingly, at different ground state, at low temperature versus high temperature, we see this crossover effect from the two phonon peaks. Essentially, one mode is enhanced at the same time the other mode was suppressed. To understand this feature better, we need to talk more about the easily perturbed magnetic ground states in calcineucinate. So this has really been an interesting topic in this material system. If we look at the ground state without magnetic field, we observe this AFM along B versus AFM along A transition. But if you apply a magnetic field along the B axis, we actually can excite a phase transition, especially near the MIT transition, called metamagnetic phases, where along the B-axis, you will actually have a modulation between bilayer ferromagnetism to anti-ferromagnetism back to ferromagnetism over a distance in the real space. So the origin of this interesting feature has been hypothesized by two main effects. One is that this MM phase is stabilized by the polar structure under weak magnetic anisotropy. And the second key feature in the system is that spin orbital interaction and anti-symmetric DM exchange actually induces this metamagnetic phases. So then we look closely to the temperature-dependent study of neutron scattering, which is sensitive to magnetic orders. We sort of see a trend that's the AFMB peak slowly dies out, and the AFMA phase increases after the temperature of the transition. But near the phase transition, we also observe we can also observe a satellite peak that's corresponding to an incommensurate phases probed by the neutron scattering. And if we correlate this piece of information to our amplitude of the asymmetric peak, we also see a clear dip near the phase transition. So clearly this Raman signal was correlated to a magnetic ground state as well as electronic ground state. So here we try to propose some further exploration of the potential mechanism of phonon energy shifts. So if we extrapolate the two phonon energy predicted by the DFT calculation, we can see in extra to the bracing mode that's modulating the octahedral cage volume, we also have the C-axis shear mode at the same time have a different phase than the bracing mode in terms of the octahedral modulation, but still very similar, have a volumetric modulation of the octahedral cages. So we're proposing some roads to study those two modes by using DFT. So the first thing we can look at is when modulating along the atomic position changes with the phonon modes. And we can calculate the density of states via spin orbital coupling along the phonon modulation and see how the density of state changes. The other key feature we can look at is how localized polarization is modulated by those two phonons.
Out of time, can you do a little bit faster?
Sorry?
You are running out of time. Can you go to summarize your talk?
I think that's my last slide. So basically, okay, we are proposing those two routes to study the interplay between the lattice charge and spin orders in the system. And with this, I'm taking questions. And if you have more questions, I can answer via the email.
Okay, so there is one question from the audience. Is phase stabilized by the induced polarization in the material or by the spontaneous polarization of ferroelectricity?
Sorry, what's the second part?
Uh, is phase stabilized by the induced polarization in the material or by the spontaneous polarization of ferroelectricity?
So in this paper, they propose the spontaneous polarization in the material is responsible for the system. Rather, the symmetry of the structure is very important to induce the MMT phase.
Another question is, how can you have a ferroelectric polarization in a metal where there are free charges, not the bound charge?
Sorry. Oh,
How can Mhm.
yeah. So in this system, because of the polar distortion, that's really stabilizes the polar structure, and it's really the displacement between the calcium and the oxygen that shows a polarization in the structure.
the last question, is your sample stoichiometric?
Sorry.
Is your sample stoichiometric?
Stoichiometry. Yes. So there's no doping or anything. It's strictly 3 to 7.
Okay, thank you. We're already late, so thanks.